Hello, it's time now for us to start talking about how to build the inverted index. The inverted index, again, is this data structure that we're going to have that enables us to do fast retrievals for the user so that we can do this in an interactive fashion. Rather than at the time of a user's query having to go through and look at every single document in a collection and parse it and everything, which would be prohibitively expensive, we build in advance index that allows us to very quickly run our retrieval algorithms. So our goal here is that we're going to be given a term ID. And again, this is coming from the user's query. We tokenize it. We go look up in the lexicon and we find, oh yeah, this token or string maps to this term ID. All right, so we've got that term ID. And we then want to be able to ask our inverted index or our retrieval engine, whatever we want to view it as, all right, give me the postings. Oh, okay, well, what are the postings? The postings is basically the count of that term in all the documents that that term occurs in. And we want, an important thing is we want this inverted index to be able to work such that it returns this in constant time. It's like, give me this postings list, boom, it gets it, it returns it, everything is good. We need to be able to fetch it quickly. And yes, it's only for the documents for which the term occurs in. So there's a huge number of documents for most terms that the term never appears in, and they would have a count of 0. They have no mention at all in this postings list. This is just merely the presence information. All right. So what does this look like? We order the things in the list by increasing doc ID. The simplest way to do this, and that's fast and compact and uses, so compact means not using much memory, but also keeping the data really together so that we can have good locality properties, which tend to improve the performance of algorithms. Just stick it all in one array. So for term I, we'll have an integer array. And what we'll do is we'll alternate. We'll go from doc ID to the count of that term in that doc. So for term I, which could be the word shark, okay? Document 3 has the word occurs in it once. Document 12 has the term occur in it once. Document 67, though, has it 3 times. Document 223 once. Document 5002, 6 times. Okay, great. And so forth and so on for the entire collection. And again, only where the term is actually found in a document. So this is what we want to build this data structure so that we get these back in constant time. We will show you here, going through things, how to do the inversion. So create this inverted index is to do the inversion. We'll do it in memory. Later in the course, I'll show you how to do a disk-based inversion. What we will do in 541 for our homeworks, and homework 2 should be out soon, is that we will do an in-memory inversion. Again, we can do this when we don't have too many documents and we keep our collection size very small in 541. So we'll be able to do this in memory, and then we'll just simply save that data structure to disk. When it comes time to actually do our retrieval, what we'll do is we'll bring the whole index back into memory and we'll have an in-memory inverted index. All right, this will allow for very fast retrieval. It also makes implementation very simple. Traditionally, our document collections have been so large that the inverted index cannot fit into the memory of the computer. And so we have a disk-based index for the inverted index. And in that sense, it's still constant time, but it does require us going to disk to fetch the postings list for every term in the query, and then pull those only those posting lists into memory, do the retrieval, show the ranking to the user. Major search engines today, RAM has become relatively affordable compared to their business models and their profit. And so my understanding is that they actually maintain at least a sizable portion of their index in memory for very fast retrieval speeds. It might be possible that they actually keep the whole thing in memory. I don't actually know. That's a trade secret. Nevertheless, that's what we're going to do. So let's continue to look at this. So this is one way to store the postings list, and it's actually the way I recommend. A very nice, just stored in an array of int. It's sized to be the right size for the number of documents. So in other words, the number of documents that you have for this term, you'll just simply need it to be twice that length because you'll also need to store the count. It's a simple data structure. It's not hard to work with. That being said, some students balk at this. They feel like, it doesn't feel right to have a document ID and a count together in the same array. Trust me, it's all good. But some people prefer to do something more along the lines of they're going to make some sort of class, and they like to make a pair. So they make a doc ID count pair. And they go and they say, all right, I'm not going to make this. So I've got some sort of public integer, doc ID, and then I'm going to do a public integer count. And then for them, they build their postings list quite simply. It ends up looking then, they have to have a reference off to an object, and inside of that object is the doc ID and the count. And so 3 and 1, and then the next one has to have a reference again to another object with its doc ID and count, and so forth and so on. What are the downsides to this design versus the previous one? Well, one of the things is that to go through the list and to access and to know what the doc ID and count is always requires a dereferencing of basically a pointer of the object reference here. So there's some added constant overhead to every single access then of needing to go through down this posting list. Basically, you're just sort of slowing down the rate at which you can process the data. You're making your search engine slower. In addition, these references here are going to be either 32-bit or 64-bit integers, depending, sizes of, not necessarily integers, 64-bit addresses or 32-bit addresses. There's a good chance they're 64-bit because everyone's on 64-bit architectures now. So you're using up 8 bytes of space for this reference. For all these posting lists, well, that's going to use up more RAM in your computer. The previous one just simply has the 2 integers packed nicely in an array. All right. Likewise as well, because these objects can be floating all over RAM, you also destroy the data locality and efficiencies that can come about from keeping your data close by. Modern CPUs are designed to be able to do things under the covers that you're unaware of, where they know and recognize that you are running down an array, and they'll be pre-fetching the array contents for you, ready for your algorithm. So there's a lot of advantages actually to the previous one, but if that pains you too much or you can't code it, students have been successful with this. It's not my favorite though, and there are downsides to it. All right, so those are what the postings look like. What does the inverted index itself look like? What is this structure that we're going to build? Well, and how are we going to represent it? It's not that hard. We are going to store, so we store an inverted index in memory using a dictionary. That maps from term ID to its posting list. And you can implement this dictionary with a hash table. Or even simpler, trust me, it is even simpler, with an array of arrays. All right. So the great thing about, again, array of arrays is that this thing is compact and fast. So this is a recurring theme in systems engineering for large systems. We have to actually pay attention to the amount of storage space that we use. We want to pay attention to some of the finer details regarding efficiency. We don't want willy-nilly just have overhead. Now, the hash table is certainly fast, okay? But its biggest properties, it's just trivially easy for most people because they're so used to working with hash tables in their modern languages. But it does use a bit more space. Not much, but just a bit. All right, and you can see how if we look at the notion of doing an array of arrays, how simple it is actually. So you're going to have some array, and you're going to have indexes for this array. So these are the term IDs, and it just holds a reference to another array, which happens to be the postings list. And so you're going to have something as follows. Again, where you've got a document, and its count, document, and its count, etc. All right. So, and then one goes off to its postings list and so forth and so on. So when you have a term ID and you stored an array of arrays, it's trivial then to fetch the postings list in constant time because you just simply have the term ID's ID and you go directly into the array to get it. I have seen students, for whatever reason, not implement it in this fashion. They'll do something where they will make some object, and they'll call this their postings. And this object will have in it a term ID, and then it will have the doc IDs and counts. And then they'll just have some data structure where they just have maybe just an array of all those objects. And then what they'll do is they'll write their algorithm, and they have to search linearly through all the terms to find the matching term. I think part of what happens there is they refused or had a lot of difficulty with this concept of being sure to represent terms by numbers. So this term ID, this mapping between string and ID, making use of this lexicon. And instead they sort of held on to the notion that they're going to use strings. And then inevitably, like, it seems to lead to design decisions that they do something where they end up doing, they don't actually get the constant time access to the postings. The moment they fail to get the constant time access to the postings, their retrieval times go to pot. Their indexing times go to pot because we actually need to look up posting lists quickly as we build the inverted index. Otherwise, that takes too long. So whenever a student comes and says, it's taking, 8 hours or something for my index to be built, usually it means they've not actually implemented a data structure that allows constant time access to a posting list given term ID. Okay, it's a trivial thing to implement. You could also, again, hash table, you key off the term ID and return the postings list if that's easier for you. All right, but just make sure that it's constant time. Otherwise, you're going to have a horrible, horrible time. So let's actually look. I'm going to give you a whole bunch of pseudocode now. Walk us through this idea of how to build this guy in memory. And now that we know our goal, we know what it looks like, we know what our data structure is, we've covered in the previous in the course how we're going to process a large file of documents. We're going to break it up into documents. We know how to tokenize those documents. We're going to look up those, map them to term IDs with our lexicon. Life is grand and beautiful. Let's build this index now in memory. All right. So the overall flow here, so this is sort of, you could say this is our main method for building the index. It's going to go, we're going to start with, got some doc ID, set to 0, and we're going to go through our collection for each doc D. So again, this is us reading through that file. First, we have to get our tokens, and we call tokenize. And we pass in that document D. Remember, we already covered this, but this is the method that breaks D into tokens. It removes any stop words. Stems the tokens. And we get back a whole bunch of nice tokens. And in fact, maybe I just misspoke. Maybe in the tokenize, we never actually turned them into term IDs yet. My apologies. I'll show you how to do that. So yeah, we know how to split them into words or split them into tokens. So we tokenize D, we get back an array of all the tokens, all the occurrences. These are not unique tokens, these are all the occurrences. All right. Then what we're going to do is now we're going to transform them into token IDs. Nicely break this into 2 steps. So let's make a method convert tokens to IDs, and we're going to pass in the tokens, and we're also going to pass in our lexicon. What is our lexicon? Our lexicon is very simply just a dictionary which goes from string to int. It's basically designed so that we go, hey, have we seen this string before? Yes, we have. It's ID number 6. And we returned ID number 6 then. Hey, have we seen this string? No, we haven't. Oh, add it to the lexicon with a new ID and return that ID. That's all it does. Okay. Then we get back now, so this is an array of strings, this is an array of IDs. And again, these are all of the occurrences. This is not down to unique things. Now we're going to convert them into counts. We want to count the number of times each word or each token or each term, whatever we want to call them. I like to call them word counts at this point, and so we're going to count the words. What is this data structure? Well, I'm going to make use again of another dictionary. We like these dictionaries. They're fast and easy to code, and it goes from a term ID to its count. So the idea here is going to be, given a term's ID, return how many times it was found in this. And so this is we're counting each unique token's number of occurrences. This is basically counting the term frequency. Then we need to save these guys to the postings. And so we call add to postings. We pass in our word counts. We pass in our document ID. And we pass in our inverted index data structure. And again, this is some dictionary. And it does a mapping from term ID to postings. All right. Someone might ask, wait a second, why is this called an inversion? Why do you keep talking about the inverted index? The reason is because when we have the documents and they come in, we have them as going from, we know very much, oh yes, we have a document and we know what words it contains. So we have it in that direction. We want to invert that information. We want the inverse of it. We want to know, given a term, what are all the documents it occurs in. So that's the inversion that we're doing. All right, then we just simply increment our document ID and we move on and we process the next document. All right, that's the high level sort of main processing that produces us an inverted index. And yes, once you get out of this loop, then it's your job to save some important data structures to the file system so you don't lose your hard work. You're going to save your lexicon. You're going to save the inverted index. Those are the really big things. Not shown here is that at the same time, you're going to be writing all the files into their different metadata folders and stuff. Now again, you already wrote the code to do that. You could decide, oh, I'm going to do this as a separate step. I'm going to write a new program that only does the inverted index now. That's fine. Personally, what I would do is I would modify the existing code that you have such that, again, it starts with the gzip file of the LA Times and goes, and when it runs, it processes each document, it tokenizes, and as well in here is the save the metadata, save the file, and so forth and so on, as well as building the inverted index. So it's one whole indexing process rather than you running two separate ones, because you would have to read through the file twice then. I think it's better just to be able to have it go once. All right, so let's break this down now and start looking at these methods like convert tokens to IDs, count words, add to postings. We've got to cover those three methods because we haven't done them yet. All right, convert tokens to IDs. Take in our tokens, take in our lexicon. So, and again, this is an array of strings, or a list of strings, and our lexicon again is our dictionary, which is goes from string to integer. All right, so here we go. Our first thing we're going to do is make a tokens ID variable, IDs variable, which is an empty list. We're basically, again, converting an array or list of strings into an array or list of IDs. So now for each token in tokens, we simply ask our lexicon if it has seen this guy before. And if it has, that's easy enough. We're going to add to our list of token IDs. So since it already has seen it, we can just simply do a lookup of it. And so this is going to return, when we make this call, this is going to return the token ID. Okay. Otherwise, or else, if we haven't already seen it, we need to add it into our lexicon. So we're not going to need a new ID for it. Our ID is simply, we ask the lexicon, how many words do you currently have in you? So we get its count. So that's going to be our new ID. Then we'll store in the lexicon this mapping from this ID. Sorry, from the token string. Map from the token string to the ID. We'll also then do the same thing we did above, is add to the list of token IDs the ID. Just to note, what is add doing? Usually these are methods that exist on lists to nicely append to end of list. All right, that's the end of that. And as simply as it is, then we're done after processing all the tokens, and now we're going to return our list of token IDs. All right, so in pretty simple code, income, an array of strings and a dictionary, and we're just going through, and if we've seen it already, so we already know what its token ID is, all right, we add that ID to this array, this list. If we haven't, we go ahead and we get a new ID. We save that into the lexicon, which increases its count for the next ID, and we add that ID to the list. And we keep processing this. This for loop is just controlling this if, and then when we've gone through and processed all the tokens, now we return our array. Snazzy. Okay. Next up, how do we count words? Well, we see the same pattern. over and over again of using these dictionaries where we look up and say, have you seen this before? Oh, if I have, I do something. If I haven't, I do something else. So again, our token IDs, this is our array of int coming in, not an array of strings. And we're going to, this time, we're going to have a dictionary, word counts, that we're going to store things in. We're going to map from the word to its count. And again, since our words are integers, we're basically counting integers, int to int. And now that words have been turned to integers, you can kind of see one of the performance advantages of them is because we have to do lots of comparisons. Like, is this a matching word? Have I seen this word before? Well, we're just comparing integers, which is a very fast operation, as opposed to comparing strings, which we have to go character by character by character to determine whether or not items are equal. And not only that, we have to do dereferencing in these languages for these strings to access. That adds space and time. So we move to integer representation and things speed up right away. Yes, not in the big computational complexity sense that they speed up, but in the real world constant time overhead that we have to do operations. Anyway, so we're going to go through, we're going to iterate through these IDs. And again, this sort of idiom, if an ID exists in our dictionary, so this is, we're checking the keys to see if that ID is there. Oh, if it does, that means we already have a mapping of it in the dictionary. So we can just simply do our word counts and our ID, and we can increment this. Otherwise, we have not seen it before, which means we've now seen it once in the list. And so we start off our count of that ID at 1. We've run through everything, we've counted everything, and now it's time to return that. Anyways, pretty simple code. Again, an idiom that you'll get familiar with whenever you want to count something. Dictionaries make that really easy to do. All right, one last method to run through, which is the add to postings. So now we'll have that dictionary of word counts. We'll need to know what our document ID is because we have to save this information to the appropriate locations in the inverted index. Not the appropriate locations, we have to save these counts for so all these different words with the doc ID, because again, we're doing the inversion here. And so I'm going to go through each of them. Here again, I'm mixing term and words and all sorts of things. They're all the same things for each term ID in the word counts. So this is basically, we're going to go through our keys. So for each key in word counts, let's go fetch what that count was. Then let's go fetch the postings. And I can see here already that I'm playing a little fast and loose with the pseudocode. If the inverted index has never seen the term ID before, there really needs to be logic here that says, ooh, dear inverted index, does this term ID yet exist in you? Oh, it doesn't. Okay, well, appropriately change yourself. So this is where using a dictionary, at least in the inversion process, can be really handy, because you just, again, you ask, does the term ID in inverted index exist or not? If it doesn't, then we're going to add that term ID to the dictionary and allocate a new postings list for it. Otherwise, we're retrieving that postings list, okay? So I'm leaving out some logic in this line here. I'm simplifying it. Obviously, I guess I got a little lazy here at the end with the idea that you should be able to figure this out. And boy, and then here I really go pseudocode lazy, and we append doc ID and count to postings. So it's like, I don't know how you're going to do that, but it's not hard. You know, you're just appending two integers to an array or to a list, and then you're done. All right. So again, some logic is actually hidden here such that if the inverted index hasn't seen the term ID yet, it's going to need to allocate a new postings list for that term. Otherwise, it's retrieving it. And then, you know, I mean, maybe I should just wrap this in a method call, a function call, something like that, and then said, oh, that's what that method does. Anyways, then we append those. Pretty nice. This is why we need the doc ID, because again, we have to bundle the doc ID with the count, and we're adding it into the postings, which is tied to the term ID. That's why we're not storing the term ID in that list, because again, everything in this postings list is the counts of that term, and we're just noting that, yeah, we see it in this document with this count. Okay, and we've gone through all the words that we found in that doc ID once we've gone through that list. And that's it then. Now you've done an in-memory inversion of your document collection. The next thing that we were going to talk about in the class is doing Boolean and, or otherwise a conjunctive retrieval. Basically, we require all of the words in the query to appear in the document, and we want to find all of those documents. I'm going to preface this by saying this is a really lousy form of retrieval, but we do it because it's easy to implement. It makes use of our inverted index, which allows you to test that your inverted index works. So it's easy to implement, tests our inverted index, and it establishes a really lousy baseline of quality for retrieval that we should be able to handily beat with a better ranking algorithm. All right, and makes the point perfectly clear once we go through evaluation that Boolean retrieval is not good. But I'm going to pause now and then resume to talk about that topic.